Welcome to ASIM Code. Hit that like button, subscribe, and let's make coding your superpower. An AVL tree is a self-balancing binary search tree where the balance of each node is maintained through rotations to ensure that the tree remains balanced, thereby providing efficient search, insertion, and deletion operations. The key idea behind the AVL tree is that the height difference, or balance factor, between the left and right subtrees of any node must not exceed 1. If the balance factor becomes greater than 1, left heavy, or less than -1, right heavy, after an insertion, rotations, either left or right, are performed to restore balance. The height of each node is updated after every insertion or rotation to reflect the changes in the tree's structure. This self-balancing property ensures that the AVL tree remains efficient with a time complexity of O log n for search, insert, and delete operations. So here we are. We are starting with a structure to represent our node. Each node has 3 important things: a key, the value it holds, pointers to left and right children, and a height. The height is super important because it's what helps us keep track of whether the tree is balanced or not. This is the key that the node will store. It's the value of the node. Pointer to the left child. It will point to another node, or null if there is no left child. Pointer to the right child. Same as left, either another node or null. This is the height of the node. It's used to calculate if the tree needs rebalancing. Here is a helper function that will return the height of a node. Why? Because when we balance our AVL tree, the height helps us determine how unbalanced the tree is. If the node is null, it means there is no node, so the height is 0. No node, no height, just return 0. If the node exists, we return its height. Now, let's talk about the balance factor. The balance factor of a node tells us how balanced the tree is at that point. It's calculated by the difference in heights between the left and right subtrees. If the node is null, we consider its balance factor to be 0, neutral. Balance factor equals height of left subtree, height of right subtree. Balance factor shows us if the tree is unbalanced. Now we need a function to create a new node in the tree. This function allocates memory for the node, sets its key, and initializes the left and right pointers to null. The height of the node starts at 1 because it's a leaf node at the time of creation. Allocate memory for a new node. Set the node's key to the value passed in. Initially, there is no left child, so it's null. Same for the right child, it's null. A new node starts with height 1 because it's a leaf. Return the new node. Alright, now let's talk about rotations. In an AVL tree, we use rotations to keep the tree balanced when it gets too unbalanced. We can do right rotations and left rotations to fix the tree's balance. X will be the new root of the subtree after rotation. T2 is the right child of X, could be null. Perform the rotation. X becomes the new root, Y becomes the right child of X. Y left child becomes T2, the original right child of X. Now we need to update the heights of both nodes, because they have changed positions. Return the new root X. Left rotation is the opposite of right rotation. It's used when the tree becomes right heavy, balance factor -1. We are shifting the right child upwards to restore balance. Y will be the new root of the subtree after rotation. T2 is the left child of Y, could be null. Perform the rotation. Y takes X place, X becomes the left child of Y. X right child becomes T2, the original left child of Y. Update the heights after the rotation. This function ensures that the tree remains balanced after every insertion. It checks the balance factor of a node and performs the necessary rotation. Right case. The tree is right heavy, so we need a left rotation. Perform left rotation. Left case. The tree is left heavy, so we need a right rotation. Left-right case. We need to do a left rotation on the left child and then a right rotation on the root. First, perform a left rotation on the left child. Then, perform a right rotation on the root. Right-left case. We need to do a right rotation on the right child and then a left rotation on the root. First, perform a right rotation on the right child. Then, perform a left rotation on the root. If no balancing is needed, return the node as is. Now, we are finally inserting a new node into the AVL tree. The basic insertion logic is the same as a regular binary search tree, but we are also checking the balance after every insert. Normal BST insertion logic. If the tree is empty, we create a new node. If node is null, create and return a new node. Insert the key into the left or right subtree depending on its value. If the key is smaller, insert in the left subtree. If the key is greater, insert in the right subtree. If the key is a duplicate, we don't insert it. Update the height of the current node. Rebalance the tree if needed. Return the balanced node. Let's create an inner traversal function to print the tree. This function will print the keys in sorted order, which is super useful to check if the tree is correctly balanced. Visit the left subtree. Print the key of the current node. Visit the right subtree. Start with an empty tree, root is null. Insert nodes into the AVL tree. As we insert, the tree will automatically balance itself. Insert 10. Insert 20. Insert 15. Insert 25. Now let's print the tree in inner traversal. This will print the tree in sorted order. Inner traversal should print the nodes in ascending order. Now run our code. Thanks for joining me. If you enjoyed, make sure to like and hit that subscribe button.